Hello, welcome to Sharknet seminar. Good afternoon and good morning, depending where you are from. Today's seminar is an introduction to parallel and the high performance processing with R. This is for those of you who have some experience with R, but not much exposed to parallel processing. For those of you who have already used parallel processing R for a while, and maybe the seminar might be trivial. But anyway, if that's the case, then I would appreciate it if you can join us and answer some of the questions from the audience. Okay. Here's the agenda for the seminar. We will quickly talk about how to run R on SHARCNet and how to run many R simulations, the SHARCNet at once. And we will spend quite a bit of time on parallel processing with R. And we'll leave about 5 or 10 minutes toward the end and talk about some other aspects of high performance computing with R. First of all, this is a SHARCNet specific. On a SHARCNet, there are two ways of running R. So one is go to a cluster, and once you're on the cluster, you load the module. You load the R module, and you start R. Or alternatively, you can go to rstudio.sharknet.ca, and you will get a online version of RStudio from SHARCNet. The advantage that I can get from this online RStudio is it's a 16 core a node, a dedicated 16 core node, and you can do parallel and concurrent processing on this node through this web interface. And of course, that you can use R Studio on your own machine if your own machine, your laptop or departmental machine have a lot of cores. But otherwise, if you want to use many cores or run many simulations simultaneously, then come to SHARCNet and you can do that. So first example, let's assume that I have 10 simulations and each will go independently, and I like to run this on the SHARCNet or elsewhere. And what I can do, I will type the submission command 10 times because I'm running 10 simulations. But if I have 300 simulations, then typing the commands 300 times is not practical. Instead, I would write a bash, a shell script to loop over the simulations I want to start. So here's an example. This is on SHARCNet, and we're using sqsub command, but if you're running the simulations elsewhere, it's more or less the same. So I'm using this shell command. I have 300 simulations. Each one of them is using the same R script, but it's taking a different input file. For instance, it's called a param, a number. I label them with numbers from 1 to 300, and this is what I'll do. I use a for loop and loop over all the input files and submit an R simulation. Now, suppose I have the input files with irregular names. For instance, the patient names. So if I have irregular names, what I can do is in this shell script, I use a slightly different format. I loop over all the files that with the extension CSV. Suppose that my input files are all in the CSV format. Then I can loop over all the those CSV files and submit my R simulations at once. So this is how I run R simulations on SHARCNet. In summary, here's a little bit different. If I'm running an R on the multi-cores, then I'm using a different queue on the SHARCNet. I use a threaded queue. This is the command. I define the queue name and the number of threads I want to use, and this is the command to submit my R simulation that will run in multi-threads on multi-cores. If I want to run R simulations across different compute nodes, for instance, via MPI, then I would submit my R simulation to an MPI queue. In this example, I'm using a 32 cores or MPI 32 MPI ranks, and submit this to an MPI queue. Now, I won't talk about much about the R and with MPI. You can refer to the documentation instructions on the SHARCNet webpage or the internet to find the details about R MPI, which is developed by Professor Yu Hao at Western University. There are a lot of details on how to set up R MPI and how to run R with MPI on clusters. But we won't talk about details here because MPI it will take quite some time to talk about the MPI, to understand what the MPI is, and in addition to parallel processing. Okay, now let's talk about the parallel processing. First, let's take a look at this simple example of a simulation of a diffusion process. So what we have here is we have a whole bunch of particles at the center, at the beginning, and we want to simulate this diffusion process over time. And we make a couple of assumptions, which you will find in the textbook, by the way. And each particle, we call the walker, will walk randomly independent of each other. And each one of them walks a small distance over a small time step. And also, at each point, each spatial point, the probability of a walker arriving at this location depends only on the equal probability of it having reached the neighboring points. So in other words, from the simulation's point of view, each walker or particle can move equally either direction. Okay, this is what it is. Now, if we're going to simulate this on a single core, and of course, for those of you who have done programming, and we will use a for loop to iterate through the walkers. Well, we have a whole bunch of walkers, and we just iterate through over them using a for loop. But if we have a multi-cores or multiprocessors, and then we might use a for each, and each core will follow a subset of walkers. Now, there are a number of parallel packages that we can use, but unfortunately, there are many. Actually, many parallel packages, and sometimes if there are too many things, then that make you choosing one, make the decision of picking one difficult. There are a number of packages, a multi-core, which enables the use of cores on a single computer, or a SNO, or stands for Simple Network of Workstations, which allows you to run the R code on a single computer and a cluster of computers. And the things are the version 2.14. There's a package called Parallel, which builds on top of multi-core and the SNO as a higher level package, and you can use. And also there are a number of other things, like for each of the packages that enables one to perform parallel for loops, and of course our MPI and a few other things. But here we will focus on the parallel package and the for each. Now back to this example, we want to simulate a one-dimensional diffusion process. Now again, the assumptions that we have is all particles start at the origin, and each particle, the walker we called, walks randomly, either leftward or rightward, with equal probability, independent of each other. And each one walks a small distance over a small time step, and each one of them at any particular point will have an equal opportunity to go either left or right. So here is our first implementation. This is not parallel. We just simply translate the idea into this our simple R code. So we are using two arrays. One is X, which contains the path in column. And now on this diagram, on the right, each column stores the path or the displacement over the history from the origin to, in this case, we want to simulate 200 steps. So first we create this array, two-dimensional array, X, and also we create another array, X2, which stores the variance of displacement. But let's ignore that for now. On the left, we have this for loop. First, we loop over walkers. And within there's a for loop, and we loop over the steps. We're going from the second until 200. So very simple. And each one, the new location is just the previous location plus a small and random displacement, either backward or forward. So this is the direct translation of the mathematical expression. This is a serial code implementation, and here this is the complete code. On the left-hand side, we have this for loop, and on the right-hand side, we do some post-processing after we simulate all the 100,000 walkers for 200 steps. Then we do some post-processing to calculate the variance over the distance and the generated plots. But let's not worry about that details. Here's our second implementation. Our second implementation, at the beginning, we load the library for each, and also we load a package do parallel. And do parallel, by loading a do parallel, we will load parallel and iterator implicitly. And these two packages are what we want. Again, we define the number of walkers and the number of steps. And now we replace the original for loop with this for each with the for each loop between register, do parallel, and the stop implicit cluster. So the first call in the block in the bold phase, register do parallel, tells the system we will create a four workers or threads or processes, and after that we will call this a for each. We'll iterate through the walkers, and then we place this operator do par. We do this for each, and we will do the following in parallel. This is what the do par stands for. So within this for each loop, we just simply simulate one path. Okay, we simulate the one path, and there's one path which is simply we have the old location and the new location of a particle. It's just we just add a small distance, a small displacement to the old to the previous location to get the new location, and this is we stored in this variable x2, and so each at each iteration we just create a vector x2. This vector x2 contains the whole path from 1 to 200. Now, for each, in fact, is a function instead of a programming construct like a for. This function will return the computed result and stored in the variable result. Okay, so the variable result now is a huge vector which contain the path or the vector x2 of all 100,000 walkers. So after the for each loop is done, we call stop implicit cluster to stop the parallel processing, and that's done. And after that, on the racking side, we reshape we extract the result and reshape the result and put it in the two-dimensional array X as we had before. Now, our third implementation. The third implementation, we have a single for loop. With single for loop, and we loop over all the walkers from 1 to 100,000. And each iteration, we generate a vector of displacement, and then we call a function COMSUM to generate a vector of displacement for a walker. So what's happening here is we're using a vectorization. So notice for each walker, the displacement for the origin can be obtained by this formula. So the next location will be the kernel location plus a small displacement. And this cumulative sum can be completed efficiently by just one shot using R's function COMSUM. Compared to previous for loop, nested for loops that we had in the first implementation. Now on the left-hand side, we have this one single for loop, and within this for loop, we simply just call two functions, an R norm, which generates the normally distributed random numbers, small displacement between 0 and 1, and call a COMSUM to generate the complete path of this walker. Okay. So now we have seen 3 implementations. If I go back, this is our first implementation without parallel processing. We're using a nested for loop. First, we loop over 100,000 walkers, and then within the loop, we loop over the path steps. Our second implementation is actually the parallel implementation. We call parallel. We load the parallel packages, and we create 4 threads or 4 processes, and we do this. We do the simulations in parallel, and our third implementation is not a parallel implementation, but instead we're calling it to R function. So what is the difference? So I put up this performance comparison here. Number of walkers, so we're going from 1,000 to 100,000. And the first implementation, we just simply use a for loop. And the second implementation, which is a parallel implementation, we're using a for each with a parallel or do parallel. And our third implementation is a serial, it's not a parallel, for loop plus cum sum. Now you can see the difference. Now, if you compare the serial implementation and the parallel implementation, the parallel implementation using a for course, we have pretty good scaling. We cut the time by 1/4 to 1/4. However, if we're using simply using the serial implementation with R function cum sum, then we have a significant improvement in the performance. So, what we're seeing here is if we're using a vectorization, the third implementation, we're using the vectorization by calling this R built-in function, and we can greatly improve the performance. So that's the takeaway message. So vectorization. So these are the functions apply. I call it xapply. These are the functions that I should use all the time whenever possible. This apply function, this family of apply function will take a vector x and then apply the function that you define to this vector x. Okay. So yeah, for those of you who are already familiar with R, you perhaps you've already used those apply functions already. Here's the example, and the passing of one argument. So when we apply and when we use the apply function, we take the first argument in apply function as the vector, and then the second one is the function we want to apply to the first vector. So in this case, our function R norm, which is our function, in this case we take only one argument, which is the n in this case. So we define a vector 2, 3, 5, and then call this apply function. So we generate a list of 3 tuples. First, we have a 2. The n is a 2, so we apply this function to a 2. We generate 2 random numbers. And the second, we have 3 random numbers, and so on and so forth. Now, what if you define a function that the function that would take multiple arguments? Well, this is a function you define. This is my experience that I had before. So in this example, I defined a function path, Remember, this is the function. That we used in our simulation of one-dimensional diffusion process. So we defined a function path which takes a number of steps. And the second argument is the origin, so where the particle or water starts. And the third one is the deviation, and that defines each movement and how far each movement, each displacement will be. So you take the three arguments. I show the three examples here. The first one, I said it doesn't work. So I call the function in this case, I call the function sapply, and I simply put my function a call to my function path, which take the three arguments. Now this call will fail. This doesn't work. The second way, it works, but not so obvious. Again, the same function I define. And in the call to sapply, I put the function name path and a comma, and then I put the three arguments as a separate arguments in the sapply call. This doesn't look obvious, but it works. And the third way, this works too, but at least consistent to the function definition. So what I do, I call the sapply, and I put the function on this slide. The function is in both phase. The function, the form of this function, and which takes the three arguments, and then I put the actual form path with the three arguments, and this works. So the second and the third methods work, but whichever work you feel better. That is use whichever one works the best for you. All right. After seeing the vectorization, now let's take a look at the another example using these functions, using these vectorizations. Now, in this example, we try to simulate stock prices. We take one, in this case, we just simulate the one stock price over 200 days, around 200 days. We set the initial price. The initial price is $25, and we try to simulate the movement of the this stock price in the next 180 days or so. And we assume that in the average of 0.1% of a gain of its opening price, and a volatility of 0.001. Now we want to generate 100,000 scenarios or paths of movement and examine the results at the end of around 200 days. That's what we want to simulate. This diagram here shows 7. I just picked selected the 7 paths from the simulation. So again, now we want to use a vectorization. We assume that the price follows a certain distribution. As I forget about what I said here, normal distribution. It might not necessarily strictly follow that distribution. Now let's assume that the daily change rate in the stock price is Q. And here the Q is already it's 1 plus a small change. So the next day price, or today's price, will be the yesterday's price multiplied by a factor. Okay, so instead of have a cumulative sum, we have this cumulative product. Okay, and we're going to use the R function, R norm, to generate a vector of a change rate over 200 days, and then we call this comprod to generate a vector of prices over time in one shot. Okay, so instead of looping over 200 days, we just call the function to generate a vector of 200 prices in one shot. So that's the idea. Now let's look at the code, the implementation on the left-hand side. We define our we define our function called the stock prices. It takes 4 variables. First is the initial price, and the number of days. The second is the number of days. Third is the average gain, and the fourth one is the volatility. And very simple. And we just translate what's stated on the right-hand side into these 2 lines of the code on the top of the left-hand side in the function stock prices. And then we simply call the R function replicate to simulate 100,000 scenarios. There's no loop. We just use the function call replicate to replicate 100,000 scenarios. So in this call to replicate, we put 100,000 first. That's the first parameter, and the second one is the actual function call. Okay, very simple. This is our first implementation. So now remember, we instead of using the loop, we're simply just use our building function, our replicate, to replicate the 100,000 scenarios. This is the vectorization. Now our second implementation. Again, we define the function, our function stock price, as is, the same as before, but this time we want a parallel implementation. In this parallel implementation, after the function definition, I call this random number generator. Now remember, in this simulation, we also call the random number generator our norm to generate random numbers. But in parallel processing, one of the important and the difficult thing is to generate the random numbers or random number streams that are independent, not correlated. Without going much details here, I just simply saying we're using a random number generator. It's got we call this RNG kind. We play this call and specify the random number generator, which is Irregular random number generator. And this random generator will guarantee, well, first of all, it has a period of 2 to the power of 191. So it's a huge period. And the second, each stream will get 2 to the power of 127 random numbers. That's very big enough. And in parallel processing, by setting this random number generator to use this Irregular random number generator, each worker or each thread will get a new random number streams. So then you don't have to worry about the correlation, or you don't have to worry about that too much. So that it does it for you. So certainly this is an advantage, and that should be used. So in this example here, I place this call to the select a random number generator, and then I set a seed. I can set I pick a 47. I just randomly for no reason. You can pick any number, and then instead of calling a replicate as we saw in the first, as we used in the first implementation, we use the MC LPly. This is a multi-core LPly. We apply the function. We define the stock prices to 100,000 scenarios. And what does MC LPly take the three parameters. First is the number of iterations. The second one is the actual function to apply, and the last one is allows you to set the number of cores to use. In this case, I set a 4. Just for the demo purpose. So after this call, then we're done. We're done the 100,000 simulations. Now just compare this to our first serial version, which is listed on the right-hand side. You will see the function definition. The two function definitions are identical, and the simulations itself are pretty much the same, except for in the parallel implementation I called MC LPly, and in the serial implementation I used replicate. Now I didn't show other option here on the on the left hand side. Instead of using a multi-core LPly, we can also use cluster as well. Cluster as well. If I have time, I can show you the actual code when I switch to command line. Okay, so this is about the example of parallel implementation along with together with the vectorization. Now, change the topic. Implicit parallelization. The R uses a lot of underlying libraries, and some of underlying libraries is already parallelized. For instance, in this matrix multiplication, the underlying linear algebra library is already parallelized. So you don't have to do anything. So the parallelization with the R, you can do. You can write your parallel code with some efforts, or in the case of the implicit parallelization, you don't have to write. You don't have to do anything. All you need to do is to change the way you run your R code. Let me just switch to a command line and just show you this little example. Just so you will get an idea, a taste, what the implicit parallelization is about. Now you might lose the slides already, but we'll get back later. All right, so let's take a look at this matrix multiplication example. I just make the size a little smaller so it will run a little faster. I define the two matrices A and B of size for the 2K, and then I time the matrix multiplication. And this is how I do it. First of all, the matrix multiplication will use the underlying math library, which is already parallelized. And first of all, let's take a look at this environment variable, open MP Now, by the way, OpenMP is a compiler-directed approach for parallelization for multi-core system. In particular, the linear algebra libraries we're using are using OpenMP or OpenMP enabled. It will look for, when we start a program, the underlying library will look for an environment variable, OpenMP num-threads. So in this case, let's see what values. Okay, it is set to 4. Now I want to change that to 1. So we're going to just run this in a single thread and see how long it will take. Okay, this is what we run the code. This will approximately take about 20 seconds. So we're taking two square matrices, about 2K, and sorry, it's not 2 seconds. It's 5 seconds. That's still way too faster. Okay, so we're using a single We're using a single thread. Now let's change that to multi-thread. Instead of 1 thread, we're using 4. Maybe using 2, and run the code again. Now see, we cut the runtime by half. So without changing the code, without changing the R code, just by setting the environment variables to tell the system, to tell the underlying library, we're using 2 threads, and then we can gain the parallel processing, the advantage of parallel processing. Then we can cut it. We can do the further we can use more threads and run it again. It'll be faster, presumably. Right. So this is just a proof of concepts that sometimes you can achieve the parallelization even without changing your R code. So next a couple minutes we can. Oh no, hold on. Let me switch to the slides. All right. So sometimes things might go wrong. This is the ugly part of parallel processing with R. For instance, in this code, I'm loading a parallel library. I'm calling I'm generating a vector called a test, and then I'm calling MCLApply to apply the function. Loose smooth, which is building function, to this vector using 1 core and the 2 cores. Okay. So what this loose smooth function does is simply just the curve fitting. You given a whole bunch of observation points, and this function loose smooth will try to fit those points. So what happened here, or what could happen, can be this. Either the code does not scale at all. Just by using more cores, you will not experience the acceleration or speed up. Or the code can simply hands. And this is a real example that we discovered in the past. And the second scenario that the code hands is more severe, because the code simply doesn't work. The reason for that is related to what we are just saying, because the implicit parallelization. So in this case, we try to use the explicit parallel feature explicit parallelization feature offered by the package parallel, along with the implicit parallelization that this building function smooth uses. The building function uses an underlying library against a linear algebra library. When you do a curve fitting, it will boil down to some linear solving linear system. And in that case, because the linear library is already parallelized, so now you have this conflict or possible conflict between this explicit parallel package and the underlying already parallelized or threaded the library. So it will cause unexpected. It might lead to an unexpected situation. So this is a bit of a warning. The dark side of parallelization with some of the R packages. You have to know what you are doing. In this case, the remedy for this we discovered, in order to make use of the parallel processing capability, we have to turn off the implicit multi-threading, and then the use of a parallel package will work. Otherwise, we will get in trouble. Now, in the next couple of minutes, let me just talk about a few miscellaneous things. First, large data sets and linear model. This is all about the high performance computing, not necessarily parallel processing. In this first example, I have a large data set, 5 million data. I want to use a linear model to fit. So I call this our building function LM, but sometimes this may fail just because this is too large. Especially on your laptop, if your laptop doesn't have enough memory and you have a large, very, very large data sets, that this might simply just fail. However, if all I need is to try to get these coefficients of this linear model, then I don't need to call the R building function LM, the linear model. So I know this curve fitting. If I know math, the curve fitting here is basically simply for this linear model is a linear square problem. So what I'll do, I create a coefficient matrix A, and the right-hand side Y, and then I simply call the R building function R.solve to solve for the 3 coefficients, and this works really, really fast. If you don't need anything else but just 3 coefficients, then this might be the way to go. Or alternatively, you can even do you can generate you can solve this problem by solving these normal equations. You define the matrix A, you define the B, what is normal equation, and then you can get the answer as well. But it's generally using normal equations is not recommended. Just an example, for large data sets, depending on what you want, sometimes you can just take a shortcut. Second example, loading large CSV files. So in this particular example, I have a very large CSV files containing data from our database, 1.7 million records, 22 columns. Loading this into memory takes about 5 minutes. Now imagine if you want to do this over and over again, multiply 5 minutes by a big factor. That's just not acceptable. So what I did, I Googled a bit, searched, and I found this solution. Someone already tried to use read, use a table, use the big memory, use FF, and use something else. And turns out, if you use the package data table and the loading a large CSV files into R could be surprisingly fast. So here's what I did. So I installed a package data.table. Now I load this into the database. Load this file into R. Now it takes only 21 seconds versus 5 minutes. Okay. Next example. After I loaded the data in, I want to sort the data. I want to do something about the data. I'm going to sort it. I want the data to be sorted by number for course use. By the way, the data I have are from our database that contain the job records. People use the job records, like number for processors, which is size of the job, and the in time, start time, and out time, and that kind of thing. So let's say I want to perform a task of sorting the data by number for a course, or we want to find a minimum, a maximum, or mean. So these operations, and the people used to procedure programming may get lost if you want to, if a given data, if you want to consider something, might be using a for loop or using some programming techniques that you're used to try to get what you want. But R is much better at this sort of things. So this is about using aggregate function, and this is what we want to use. Using aggregate function, we can do things like a sorting by number by some column, and it can be very fast without much programming effort at all. So here's the result. I counted number of jobs sorted by the number of CPUs. This is what I accomplished. The next, the large data out of and out of a core operations. Let's say now if you have a large data set, well, in this case I have a 1.5 gigabyte of data and 34 million records that cannot or can easily fit into the memory. Here's an example. After I load the data into memory, it shows now it's taking 700 megabytes memory. If my computer doesn't have that enough memory, then I'll be in trouble. So this is why we want to use the out of core operations. We use the package big memory. If we use the big memory and we compare the memory usage before and after, before and after we loaded the data, it only takes 7.4 megabytes as opposed to 700 megabytes. But loading the data does take a bit of a time. However, after the data, now remember, because we're loading a huge amount of data in, so we have to have some trade-off here. Loading the data it takes much time, but after we load the data in, now this is then we perform out of the core operation, and these operations are actually quite fast. So just wrapping up, I just put a list of upcoming or potential workshops. Here we go, and I stop here, and we have maybe a couple of minutes to take questions from an audience.